We're here again. I hope you caught the tail end of the keynote and where we, came out of stealth. If you didn't, it was a doozy. I'm happy to do this all over again for you. So I'm Mehul Shah. I'm the CEO of Aaron, and John Fritz here, who's sitting down, is the the Chief Product Officer of Aaron. And today we're going to show you how to build conversational search apps using Aaron. A little bit about us. We're database and big data people from Amazon, Google Cloud, Meta, and our mission is to answer questions from all of your data. And we're doing this by helping to bring generative AI to OpenSearch. And one of our goals is also to expand and grow this community, the OpenSearch community. What I announced this morning was Aaron's new offering, a conversational search stack. It's open source, and it makes it easy for developers to build and scale conversational apps on their enterprise data. So this is the agenda for today. I'm going to first motivate why we think customers want conversational search, why they're telling us they want conversational search. I'll go over some techniques for building conversational search. Then I'll dive deep into the features that we've added to make this possible in OpenSearch, as well as dive deep into our new semantic data preparation system called Sycamore. And then I'll wrap up with some emerging use cases for conversational search. All right, how many of you have tried some generative AI model? Raise your hand. Okay, for those of you that didn't raise your hand, why not? It's super easy. Just go to ChatGPT. That's a generative AI model. There's a whole bunch of them. Bard.google.com, Bing, lots of different places where you can try these things. And these things are absolutely amazing, right? You just type in something in English, whatever language you're comfortable with, and it can really mimic human behavior in certain cases. You can get it to tell you a joke. You can tell it to write a limerick for you, respond to an email, summarize Don Quixote. I mean, it's just amazing what it can do. And we actually noticed this trend a while back. You could see the number of parameters that these models had and how fast they were growing. And you can see that that's a Richter scale, right? It's logarithmic. It's going up actually more than, in the early days, more than 10x per year. And now it's starting to trail off a little bit. And it's important to understand that at some point, these things are going to need other mechanisms to be able to continue to get better and better. What's more important here for us, however, is their ability, and we're calling these things, the kinds of models that we're interested in are large language models. What's important for us is their emergent capabilities for processing unstructured data. These are things like information extraction, summarization, question answering, content generation, and more. And it's sparked the imagination of a lot more than just us, but just people across verticals in industry. We have customers in the financial services space, an investment firm, where analysts need to go through swaths and swaths of research reports, both internal and external, to put together investment theses. Manufacturing firm that has tons of manuals for parts that they've built over the years, and they want to make it easy for their customers to find the parts that they need and how they interoperate. And there are many such use cases. And the emerging paradigm to help solve these use cases is what I like to call conversational search, or chat with your enterprise data. You see, people want to build conversational applications where users can retrieve relevant data from their repositories, summarize that data, synthesize answers from that data, and in the same context, ask follow-up questions, okay? And the kind of data we're talking about are not just logs. We're talking about unstructured data like PDFs, presentations, spreadsheets, and so on. And there's tons and tons of this everywhere in all the enterprises. And a lot of this today is untapped. And they want to use generative AI models to get value from this data. All right, so let's talk about how people are actually building these stacks. The sort of traditional approach right now is to use the generative AI models directly, right? We're going to put generative AI models at the center of our universe. We're going to start talking to them, take them off the shelf. So these are things like OpenAI's ChatGPT or GPT 3.5 or GPT-4 models, or Anthropic's models or Claude's models, or you can go and take an open source model like Llama 2 that came out of Meta, and you start asking it questions. And these things are trained on public data, so they look and they do amazing things, but they're not going to work for enterprise use cases. Okay. They don't know anything of your data, nothing. But they will confidently give you an answer that's incorrect. And it's also known as a hallucination. Training these AI models is really prohibitive for most places. You need a lot of data, a lot of training data. You need a lot of expensive hardware and expertise. It's too difficult. And so instead, what we're seeing is people are bringing data to the AI models. They're building these new architectures called retrieval augmented generation, or RAG for short. And what they're doing is they're taking their data and they're chopping it up into pieces and indexing it. And when somebody asks a question, on demand, the system retrieves the appropriate chunks, presents it to the model, and the model then answers the questions from what was retrieved. Okay. And when you actually focus the model or constrain the model on very specific pieces of information, it actually does a pretty good job. So you get much higher quality answers. And so we see customers building these complex search stacks out of Gen AI toolkits and vector databases today. They're in their infancy, right? So you can get proof of concepts running, but they're hard to scale and maintain and manage in the long term. And that's only part of the problem. The other part of the problem is, how do you get the good data into these indexes so they can then be presented to the generative AI so they give you good answers? And today, most people are basically left hanging on their own to solve this problem. And so we at Aaron, we're going to go back about 50 years to when, relational databases were born. You see, Ted Codd was the father of relational databases, and he had a very simple but powerful idea. Okay? His idea was, let users specify in a concise, high-level language what they want from the data, and the system should automatically figure out how to compute that answer. And the other sort of piece of insight was that and that language at the time was SQL. The other piece of insight was that for any SQL query, you could actually compose into a pipeline, a data pipeline, if you will, these very simple operators that would answer that query. You could always find a pipeline that could do that. And this has been what has driven the relational database industry, this little insight, the relational database industry and the data warehousing industry for the last 50 years. Okay. He had another project for asking natural language queries over unstructured data that didn't go anywhere at that time because obviously the technology wasn't ready. And so now enter LLMs, or large language models. So our perspective is different. We're data people, we're database people. And what we see is pipelines. And if you kind of dig into any of these sort of search stacks, it's just a collection of data pipelines. Okay. And our approach is, let's bring the AI of your choice to the right stage in the data pipeline to solve the task, to make that task easier and to make that task better, so solve it in a better way. The second insight that we had was, hey, when we're using this, there's a stage that was missing. And that stage is the data preparation stage. And we think the developers, now that these LLMs are available, these generative AI models are available, developers can actually very easily bring the AI of their choice because they're so easy to get working, because you can simply prompt them to do the task at hand as opposed to trying to train them. So now's the time where you can actually bring the best of both worlds together, the LLM world and the search world. Okay? And so this is where Aaron comes in. We're giving you a one-stop shop where you can basically build conversational search apps. At the core of what we have is OpenSearch. It's the tried and true open source enterprise search engine that y'all are familiar with. Okay. Thousands of customers use it every day in production. Thousands of developers use it every day for their projects. They can, the nice thing about using something like open source is because it's enterprise ready, you can get to production faster. What we've done is add integrated conversational capabilities into OpenSearch, in particular version 2.10. We've added a conversational memory component that allows you to keep track of the interactions in all your conversations, as well as a RAG search processor that orchestrates interactions with LLMs to synthesize answers from the retrieved results. Now that solves part of the problem, right? But the other part of the problem, we've introduced a brand new open source project, Sycamore. It's Apache v2 licensed. It's a scalable semantic data preparation system, purpose-built for search. It is a Python native system for processing unstructured data using LLMs so that you can bring good quality data to LLMs to answer your questions. So it's the thing that's going to give you higher quality. So I'm going to hand it over to John now. He's going to give you a quick little demo of the Aaron stack in action.
Thanks, Mehul. All right. Let's see, live demo. Let's see how this goes. So I'm John. Want to run you through a quick demo app we built using the Aaron conversational search stack. And we created a quick React front end. This is running on all of those components that Mehul just talked about that we're also going to get into with a little bit more detail in the coming slides. But figure, hey, let's show what it does first, then get into how it works. So for this data set, we figured, hey, we're data people. It would be a fun data set to use. We actually took the data set from the sort benchmark competition. Let me just quickly show you what I mean. So sort benchmark, it's a contest for different teams try and sort a data set the fastest or at the lowest cost. A lot of things like Apache Spark and Hadoop have run through this contest. So we took this data set. This data set's pretty diverse. As you can see here, we've got HTML web pages with some kind of oddly formatted tables. We're going to have to go and search over that information. And then a bunch of research papers as well, PDFs like this one. You can see there's text, there's charts, there's graphics, and tables as well. So PDFs, HTML, variety of different sorts of data within them. And that's the data set that we pulled down and then put through the Aaron conversational search stack with Sycamore and OpenSearch. So let's ask some questions on it. So let's start out. Let's create a conversation here. Let's call it demo convo. We'll see how well I can type and talk at the same time. All right. So we created a conversation. You can put this away. Let's ask a question. So let's say, what are the sort benchmarks? So as you can see here on the right-hand side, we're pulling the direct hybrid search results directly from OpenSearch, and you'll see you can click through and it will highlight some of the relevant sections. These are the passages that through hybrid search we think are the most relevant. Then what we're doing is we're taking some subset of that, and you can configure that down here in this demo app, passing it to an LLM and getting the actual natural language results, which is kind of the end of the retrieval augmented generation process. As you can see here, we get an answer, direct answer, gray sort, cloud sort, a bunch of other information here on the different sort benchmarks as part of that conversation as well. So let's ask a follow-up question. Let's say, who are the latest winners? Now, as you can see here, we're rephrasing the question based on the overall context of the question, right? Like, it's not obvious if you didn't have the context. I was talking about the winners of the sort benchmark, but this whole system utilizes conversational memory to be able to keep the context of what we're actually talking about and rephrase the question to get the best results. Once again, we get a set of information here on the right. You can click through and see kind of where this information is. And then it talks about some of the latest winners here in the context of the conversation. Now, we can utilize different LLMs in different stages of the pipeline, right? Sycamore and some of the other ones. For the RAG process, once again, it's configurable. So for the rest of the demo, we can say we want to use GPT 3.5 Turbo. So I'm interested in learning a little bit more about what LSAR is. It's brought up here. I want to learn a little bit more about it. And so I'm going to ask, tell me more about LSAR. Once again, we're rephrasing the question based on the context, coming up with the hybrid search results here, so you can click directly into the source data, but then also, once again, answering your question with a natural language answer. So let's ask one more question. I'm kind of curious, how much LSAR hardware components cost? The sort of benchmark has to do with performance and also cost. So let's ask, what are the hardware components of LSAR? And let's format it as a table. So show as a table. Now in this demo app, we're not kind of rendering tables in a rich way, but as you can see, hopefully it'll come back in a way that you can imagine. Well, you could, right, and do a bunch of other different visual things with the natural language interactions. Once again, we're getting the results back from OpenSearch and then utilizing GPT-3.5 Turbo with that kind of result set to go and generate the answers. You can see here, we've got the hardware components formatted nicely. And we can actually go and click through and see, hey, well, where did this table come from? So let's go to the first search result. Let's open this PDF. Might take a minute to open based on the internet speed here. So let's give it a minute. Okay. And as you can see here, it's highlighted the table and found the relevant table with that information in the document. And the reason that the search stack can do this, in part, is because of Sycamore. Sycamore, when it processed this PDF, is able to extract tables, convert them to CSV, and kind of extract different parts to make it so that farther down in the pipeline, OpenSearch and the retrieval augmented generation process can go and get the right sets of information out and understand what this table is and the content that it has. So with that, that's a quick demo of the search stack. I'll pass it back to Mehul.
Thanks, John. That was excellent. So, being able to process PDFs that way, get into the center of all the guts of the content that's in those PDFs and make sure that that content isn't just, scattered everywhere so you get garbage answers. This is what our stack is about. So let me just kind of give you a quick little, what are the benefits of our stack? The first thing is it's a one-stop shop. You can get to production faster because you get everything from, ingestion to conversational APIs in one place. The second thing is the semantic data preparation, which we're going to dig into as well to get you higher quality answers. And the third thing is that it's 100% open source. So it's easy to customize. You can start building your projects with this, embedded in your environments, and of course, no vendor lock-in. Okay, so double click on the architecture. Now this is where we actually get into guts of what Aaron has. I'm going to go left to right. Sycamore is the semantic data preparation system. It's actually built on Ray, which is a distributed system for running Python programs effectively. And so it's built on that. It coordinates the interactions with the generative AI models to be able to do all the data preparation. It reads automatically, kind of crawls and reads your information from cloud storage. Today it reads from Amazon S3 and your file system, but we plan to expand that. And then we also plan to expand it further so that it can go after other repositories of unstructured data. Then on the right-hand side is OpenSearch. Now you might be familiar with OpenSearch, but there's a lot of new features in OpenSearch. In particular, the vector-based indexes that Eli talked about for KNN retrieval or for semantic search. They also added neural search, so you can do semantic search inside of OpenSearch itself. So there's a bunch of different search strategies that are out there. And most recently, I believe in OpenSearch 2.9, they released search pipelines. This community released search pipelines that allows you to compose different search strategies. And this is where we come in. We've added two things to this ecosystem. One, which is the RAG search processor that coordinates the activities on the front end side for getting synthesizing responses from LLMs, and then a conversational memory module or plugin that allows you to keep track of the history, which is important to be able to get the right answer and do the question rewriting that we saw in the demo. So digging in, let's talk a little bit about how the RAG search processor works. It's actually pretty straightforward. The nice thing is it's integrated into OpenSearch. So it scales, works with all of your security policies. It you don't have to worry about all the details of actually making it production ready. So the RAG search processor is basically something that you add at the end of your search pipelines. The recommended way of doing doing semantic search these days is to use neural search, which looks at embeddings over the documents that you've indexed. Embeddings are a way of capturing the semantic information of the documents and their pieces, their chunks, the highlighted pieces that you saw, as well as term indexes that you see from Lucene, that you're familiar with every day. The idea is to combine both results from the embeddings that you get through neural search, as well as the results that you get from BM25. They're just sort of term-based search. Combine those two things and then feed in those results to the RAG search processor. The RAG search processor will then get relevant context from the conversation that you've had. Most recent K, for example, interactions, questions and responses that you've given to the system. It'll then send that to the generative AI. It can be locally hosted, or it could be a remote AI system like OpenAI's GPT 3.5 or GPT-4 that we showed you. The response comes back from the generative AI. We then log those responses as another interaction in the conversational memory. And then that response is also appended to the search results so that the application can then present it the way they want with the user, and then they can iterate. So pretty simple. The other nice thing about having a RAG search processor is you can compose it with all kinds of different search strategies. You don't have to use BM25 or neural search or any one particular thing. You can build your own. Okay. So what does conversational memory look like? Well, exactly what you would expect. We keep track of a number of conversations. Okay. All of this itself is actually implemented with a index inside of OpenSearch, so it's scalable, fault tolerant, reliable, and available, and so on. So these conversations are basically a collection. Each conversation is a collection of interactions. Each interaction is composed of an input, the question that you might be posing, a response that came back from the generative AI model, the prompt template that was used to prompt the model to get the answer, as well as any other metadata that the application wants to store for that particular interaction. And then, of course, you have your standard CRUD APIs to be able to retrieve, update, and delete the interactions that are in your memory. Okay, so those are the two pieces that we've added. With that, you can start building these kinds of applications. We recommend that you go try it yourself. Let's move to semantic data preparation with Sycamore. So what is Sycamore? Well, Sycamore is basically a scalable data flow system. It allows you to prepare unstructured data to get high quality answers from your LLMs. And its programming model is very similar to Apache Spark's. Okay? At the core of it, what you have is a document set data structure, distributed data structure, and you can use LLMs on that data structure to segment, do information extraction, entity extraction, create embeddings that would then go into OpenSearch. It's Python native, and the reason it's Python native is so that you can work with all of these different kinds of AI models that are also Python native systems. And then, of course, Sycamore can today read from your cloud stores, and we hope to be able to expand this further. So what is a document set? Now, it's a distributed data structure, kind of like a data frame, if you're familiar with that from Apache Spark. It's schema-free, so each document can have whatever schema it wants. A document is really just a collection of elements. Elements are various chunks of the documents that you saw on the screen. Okay? And each document also has a list of properties. This is metadata that we're keeping track of that we want to lift as sort of first class that we can use for search and for retrieval. Elements also have properties. And the transformations you can build with Sycamore will take a doc set and then return another doc set. Okay? And you can do very simple transformations like filtering and removing certain types of elements, getting rid of stop, getting rid of like boilerplate that's in your documents. Or you can do more complicated transformations, like things that you would do to extract extract out titles and authors from papers. So these are things that you would use a generative AI system for. And then, of course, and because Sycamore is built on Ray, you automatically get a scalable parallelized automatic parallelization out of the system. Here's an example of what Sycamore can do. I showed this in the keynote, and I'll walk through it again. On the left-hand side is a research paper, and what we've done is run a series of transformations, segmentation to go and pull out these, coherent chunks that we called elements. We've also run entity extraction to pull out things like titles and authors that you can use then to directly search over the data. And then we're going to then convert all of this stuff. Sorry, we're then going to run another model to create or capture the semantic meaning of these elements through an embedding model, an LLM that allows you to give you a vector that represents the meaning of the data. And then you can then turn that into documents that you would store into OpenSearch. So this is what John is going to show you now. He's going to demonstrate Sycamore.
All right, well, let's see if we can go 2 for 2 on demos working today. So thanks, Mehul. Quickly to show you just a representation of what Mehul described on a sample Sycamore workflow. And so for this, what we're going to show is processing 2 documents. So 2 PDFs. Figured it'd be fun to process the PDF describing the article on Ray, which is what Sycamore runs on. And then the Transformers paper, attention is all you need. No introduction needed for that one. Okay, so as you can see here in the first frame in this Jupyter notebook, we're just going to kind of initialize Sycamore and then create a doc set, the main data structure for Sycamore, with these 2 documents. So let's go and play this. And this is running on the laptop, so you can see it's going in real time here. You can see the output of this is 2 documents in the doc set. No elements yet. We haven't really broken anything apart. You can see the properties of these documents, and then that they're represented as binary in these two things. Okay, so next is kind of one of the main operations here, which is the partitioning command. We're going to partition the doc set, and it uses open source libraries. In this case, we're using one. There's many different ones you can choose depending on what you're trying to do. And this code right here is really just to show the output in a graphical representation, similar to the image of the PDF showing boxes around the different elements and how Sycamore has identified them to break them apart. So let's run this. And give it a second to run. All right. And so we've processed these 2 docs. As you can see here, we've drawn boxes around just to visually represent the way that Sycamore has gone through and identified the different components in these different documents. You can see identified the title, authors, an abstract, and chunked up different parts. As you can see here, we've added all of those parts as elements into the doc set. As you can see, 254 and 580 for the other one. The next set, what we're going to do is use entity extraction to go and extract the different parts and add them here. As you can see, this is a prompt template to generative AI model. In this case, we're using, I believe, OpenAI to do this. And this is basically kind of training or telling the OpenAI model exactly what we want it to do and then giving it an example. And as Mehul pointed out, this is incredibly powerful because you can utilize a variety of different prompts to start extracting and processing your data in different ways to prepare it for search. In this case, we're training it to understand really how to extract a title and an author and giving it some examples to show, hey, well, this is how you would do that. And then we're going to go apply that to our own doc set. So let's, I think I already played this one. So let's actually go and run that. So we sent the prompt, and we loaded the prompt already. Now we can go and run it. As you can see, extracting the entity of title and extracting the entity of author, utilizing this method with generative AI. So you can see here, it worked. We've extracted the title and authors for each using this method. Okay, so next what we're going to do, now that we've extracted the titles and authors and also broken apart in elements, is explode the doc set and basically bring them all into the top level, but then each element having its parent document also noted. And that's going to help prepare it for the next step, which is getting the vector embeddings for each of these chunks. So as you can see here, before we started with 2, that was the 2 main documents with all the elements in a lower hierarchy. Now we've brought everything up and have 836 elements. So the final stage here is we're going to go and create vector embeddings for each of these elements. In this case, we're using a model, a mini LM. It's an open source model. This is pluggable. You can choose to use a variety of different vector embedding models to go and do this. So we'll hit play. While it's going, I can say that the next step here would be then loading these vector embeddings into your OpenSearch cluster. As you can see here, it looks like it finished, and you can see the embeddings have the dimensionality of the embeddings and a bunch of other information about that. And the next step would be loading it into your OpenSearch cluster and then preparing it for conversational search to the rest of the stack.
Thanks, John. You can see how simple it is to just, go and process a bunch of PDFs. With a few lines of code, maybe a dozen lines of code, you can go through lots and lots of, unstructured data and get it prepared for conversational search. And this is all possible because you no longer need to be a machine learning expert to use machine learning. Now, all of this stuff runs on it's not Apache Ray, sorry, it's just a Ray project. All of this stuff runs on Ray. This is a fault-tolerant data parallel system, and it allows you to run on my laptop, but also run across hundreds of machines. And you can see a very simple experiment where we processed about 1,000 PDFs, and you can load it. You can load it into OpenSearch, and it scales linearly. Okay. The other thing that Sycamore does for you is automatically schedule these transforms on the appropriate hardware. So whether it needs CPUs, GPUs, or some various mix of the 2 types of hardware. Well, there's a lot more left to do. Sycamore is an open source project, so we welcome you to try it out and join us. We have a bunch of things on our roadmap. We definitely want to add crawlers to the system that can go over more than just S3. We want to add other cloud stores. We want to add crawling of web pages and also auto ingestion. We want to add additional data types, images, for example, different kinds of document types, add new connectors to new data sources where your unstructured data might sit, and finally add a ton of different transformations, deduplication, for example, different kinds of segmentation so that you can keep tables and figures intact. All right, so to close, let's talk about what people are using conversational search for. We see 3 main use cases. The first one is research and discovery platforms, and this actually is useful across a bunch of different industry verticals. In the financial services space, people are gathering, internal sales data, investment data, external analyst reports, call notes, logs, and putting it all in one place so that you can discover new markets, new companies that you want to invest in. In the pharmaceutical space, it's PubMed or medical publications, internal clinical trials, other internal research that these pharmaceutical companies have, and they want to combine these things to figure out what markets to go into and what kind of drugs to develop for those markets. And sort of these examples go on and on. It's a combination of internal highly valued assets as well as external highly valued assets, bringing it together and tapping it for its potential. Another set of use cases is really just around workplace search. You got your wiki notes, you've got your internal websites, PDFs and PowerPoints that you've made over the years, and your SharePoints, spreadsheets. You want to find out, you want to find out what you've done in the past, or what one of your colleagues has done in the past, or you might want to collaborate to create something new. And just finding those things is increasingly difficult, and people are building these conversational search systems to be able to find those things and get answers for them. And then finally, the third class of use cases that we've seen are querying knowledge bases. So FAQs, forums, documentation, support tickets. Makes it much easier to support your own customers if you're for example, a SaaS service and you want people to be able to very quickly use the APIs that you have. Or, imagine you're providing some kind of, level of support, and you want to go through your support tickets to find out, what actually happened when a customer is coming to you. So these kinds of use cases are coming about. And I'm sure more and more use cases can come about over time as people start using this. So we highly recommend you come and build with Aaron. It's an easy one-stop shop, includes OpenSearch, Sycamore, and combines these things with generative AI, which are very easy to use for various different purposes and tasks. Bringing those things together will make it easier for you to build these conversational applications. With Sycamore, you can get better data into your systems to get better, higher quality answers out of your LLMs. And of course, all of this is 100% open source Apache v2 license. So you can build as you see fit without any vendor lock-in. If you want to learn more, please go to these websites. Go to our website to get started. You can go to GitHub to check out Sycamore and fork it or download it to use it. Send us feedback through these emails. But more importantly, you can see more of these demos and talk to us outside at the tables. Come try out our software. And then finally, help us make the system better by contributing.